This question is about spectroscopy. Compound K has a molecular formula C4H8O. Figure 5 shows the infrared spectrum. Which functional group does K contain? So remember, with infrared, we're going to use table A on the data sheet. We're going to ignore below 1500, the fingerprint region. This is our CH bonds. We need to get good at recognising that kind of sharp stabby peak at 3000 as being the CH. This is the peak that we need to identify to be able to pick the functional group. This is quite a strong absorption at 1700. This is a C double bond O. So it's not an alcohol, it's not an alkene, it's not an amine, it's a carbonyl, that's an aldehyde or a ketone. Nitrile is C triple bond N, amine is NH, alkene is C double bond C, and alcohol is OH. So it's a carbonyl. Compound L has a molecular formula C4H7NO. So again, let's cross out 1500. Here we've got a C triple bond N, and this is our CHs. So this compound reacts with H2. So when that C triple bond N reacts with hydrogen, we end up with a CH2NH2 at the end of our compound. To give compound M, the nickel catalyst is our kind of clue to the reduction, nickel and hydrogen. Suggests 3 ways in which the infrared spectrum of M is different. So we'd use our table A on the data sheet. So the peak, and you use the data sheet numbers at 2220 to 2260 centimetres to -1. Due to the nitrile, C triple bond N disappears because we're getting rid of the nitrile functional group. What do we get instead of that? Instead of that, a peak, we want to look up the amine peak, and so you go to the data sheet and it tells you 3300 to 3500 centimetres to -1 due to NH appears. You're thinking, well, I've got 3 lines here and I've said everything that's going to change. The other thing that will change is the bit that you've crossed out. The fingerprint region is unique to each compound, so the fingerprint region will be different. Okay, figure 7 shows the 1H, so the proton NMR of Q. So we're now going to use another section of our periodic table. So we're using our next table on that middle page. So we're stopping looking at infrared, we're going to now look at proton NMR. And we're going to look at the information that we've been given. We're going to look at this integration value. And remember, in total we've got 7 hydrogens. At the moment, 0.6 add 0.6 add 0.9 adds up not to 7, does it? Because our integration value is 0.6 add 0.6 add 0.9 is making 2.1. How do you get from 2.1 to 7? So on your calculator, you can divide it through. It's times 3.33 recurring. So if we times that by 0.6, we know that this integration is actually 2 to 2 to 3, and now it adds up to 7 hydrogens. So the peak at 3.95, that's representing 2 H's. The peak at 3.65 is representing 2 H's. And the singlet peak here is representing 3. Okay, so let's write that down. The integration ratio is 2 to 2 to 3, not 0.6 to 0.6 to 0.9. And then let's take each peak in turn. I'm going to start at what I call the interesting end. The left-hand side is the more interesting end. So delta 3.95 is and we can look at it, and it's a triplet integration 2. We've already said the integration. Then we would need to look on our data sheet. And what it says for around about 3. Sort of in the 3 to 4 region, and remember we've got Cl and an O in this compound, and this is 3.95, is that this is possibly the RCH2Cl, because anything with an oxygen The one that is 3.95 would have below it in the table B has got 2 oxygens in. We can't have 2 oxygens, and the one above it is just below 3.95. So I'm going to say it's a type RCH2Cl, and integration is a 2. So represents CH2Cl, and it's a triplet, so it's next to CH2, because to be a triplet you need to be next to 2 due to the n+1 rule. And then we've got the delta 3.65, and that's another triplet. So when you have 2 triplets, you know you've got 2 CH2s together. So it's another triplet, integration 2. But it is just that little bit lower at 3.65, so it's type ROCH. So what that represents, so we know that there's 2 on this environment, so it's an O with a C with 2 H's, that's the integration 2, and it's next to, because of the splitting, another CH2. And then the delta 3.35 is another one similar. It's a singlet integration 3, and it's another one of these OCHs, but this time it's an OCH3, no adjacent H's, and so our structure overall equals, so we've got this CH3 next to an oxygen from our bottom piece, which is next to a CH2, which is next to a CH2, which was our first piece. In an exam, I would have used some of the additional paper to finish that off, just so that I've spread it out and it's clear. I wouldn't want it to get cut off in the scanning.